This is the last video on forces. We will discuss how forces can cause objects to move in circles. Let's revisit Newton's first law. Newton's first law states that unbalanced forces cause acceleration. They cause objects to speed up, slow down, or change direction. Here we have a moving asteroid. It feels no external force, so in accordance with Newton's first, it has to keep moving in a straight line at constant speed. For something to move in a circle, it needs to feel a force. Here is the moon in a circular orbit around the Earth. It clearly feels the pull of gravity from the Earth, so why doesn't it simply fall in and collide? Well, let's think back to our cannon puzzles from kinematics. Remember how we had to solve for the motion in x and y, but the gravity only played a role in y? The motion in x was not affected by the gravity at all. Similarly, in this configuration, the moon feels the pull of gravity in the y direction, but it's already moving in x, so it accelerates in y just like the cannonball. But unlike the cannonball, the moon is moving so fast and is so far from the Earth that its velocity makes it completely overshoot the Earth. So it ends up here. At this point, its overall velocity will now point somewhat downward. That's not surprising. The cannonball did something similar when we calculated its final velocity. What's really interesting is the moon still feels a force from the Earth, but that force is no longer pointed in the y direction. It's angled so that it's now toward the Earth. So, unlike the cannonball, the direction of the force, and therefore the direction of the acceleration, has changed. Now, the process starts all over again. Once again, the Earth will pull on the moon, and it will accelerate toward the Earth. But the velocity will make it overshoot the Earth. So the moon will end up here. Its velocity points like this, and the gravitational force and the acceleration point like this. The moon gets pulled toward the Earth again and overshoots again. Throughout this process, the moon's speed doesn't change. The size of the velocity doesn't change. Only the direction changes. As this pattern of acceleration toward the Earth followed by overshoot continues, the moon traces out a circle at constant speed. This is uniform circular motion. Circular motion at a constant speed. That constant speed is also known as the tangential velocity, and it is symbolized with v sub t. In circular motion, the force must keep reorienting to keep pulling the object towards the center. Such a force is called a centripetal force. Centripetal force isn't a force in its own right, the same way that weight, normal, tension, friction, spring, and applied force are forces. It's just the name we give to whichever one of these forces is pulling the object toward the center of the circle. In the case of this moon, that's gravity. But in other cases, it could be tension, static friction, normal, or something else. Since forces cause acceleration, the centripetal force causes centripetal acceleration. The object accelerates toward the center of the circle even though its motion is tangential. And in uniform circular motion, there is a very specific relationship between centripetal acceleration and tangential velocity. Centripetal acceleration equals tangential velocity squared divided by the radius of the circle. Let's apply this to different situations. The simplest type of question involves just one force acting as the centripetal force. Here, we see an astronaut playing with a yo-yo in space. The tension in the rope is the centripetal force, and the yo-yo is not subjected to any other forces. Consider this question. An astronaut swings a 3-kilogram yo-yo in space. The string is 0.5 meters long. Its speed is constant at 1 meter per second. What is its acceleration, and what is the tension in the string? We'll start by drawing a picture. This is a side view of the object when it is at its furthest left position. Now, let's draw the free body diagram. In the positive x direction, there is tension. The total force in x is represented by the tension. This, in turn, is equal to mass times acceleration. But for an object in uniform circular motion, we can solve for the acceleration. It's equal to v squared over r. In this case, that works out to 2 meters per second squared. We can use this information in the force balance to work out the tension. It has a magnitude of 6 newtons. This is the centripetal force required to keep the object moving in a circular path. I'm going to draw 2 pictures of the setup that we have here, a top view and a side view. So this is just for clarity. You don't have to do this in your homeworks. But let's start by drawing this object over here, this turntable, and let us draw an object which is sitting on top of the turntable. So the turntable is going to spin like so, and the object on it is going to spin like so as well. Now, this is the top view. We can imagine this object tracing out a circular path as the turntable spins. If we were to take a look at a side view of it, the spindle would pass something like this, and this object which is sitting on top would look something like this. Now that we have this side view, let us draw the free body diagram. This object is going to feel the customary weight down, normal force up, and if it is sitting over here and moving along with the rotating turntable, then what force is responsible for it actually moving in a circle? The static friction. Because the object is not sliding on the surface of the turntable, it's moving with the turntable. Had there been no friction, the turntable would have just rotated under the object, a little bit like those magic tricks where someone whips a tablecloth out from under all the cutlery. So this is moving with the turntable, which means that since it's not sliding, it's feeling static friction. And the static friction is the thing which is responsible for the centripetal force, or the static friction is the centripetal force that's going to cause this to move in a circle. Now, let us apply the origin, always at the center, and the axes. I'm going to set upwards as my positive y, and rightwards as my positive x. Now we are ready to set our, to find out how big the forces are. We're ready to set our force balance. We have to start with the y direction, and the reason is we have a static friction here. A static friction can only be calculated using the normal force, so we need to find out how big that normal force is first. So in the y direction, we have total force is equal to normal plus negative weight, but total force is also equal to mass times acceleration. So putting these two together, I get normal force plus negative weight is equal to mass times acceleration. Now let's figure out how big the weight is. In fact, before we go any further, why don't we list out what are the things that are known in this question? We were told that the distance of the object from the center was 0.2 meters. The mass of the object is 0.5 kilograms. And the coefficient of static friction is 0.3. We will use all this information at various points in this puzzle. So the weight force is going to be equal to mass times gravity. Mass, 0.5, times gravity, 9.81. That works out to 4.905 newtons. So we now have normal force minus weight force of 4.905 is equal to the mass, 0.5, times the acceleration. But this object isn't moving in the y direction, it's not collapsing into the turntable, and it's not levitating off the turntable. Therefore, acceleration is 0. So this entire right side becomes 0, and the 4.905 can be moved to the other side, so we end up with a normal force is equal to 4.905, and because it's pointed in the positive y direction, we'll put it as 4.905 j hat newtons. Now, let's take a look at what's happening in the x direction. In the x direction, the total force is composed of only one force, and that's the static friction. So that means that since total force is equal to mass times acceleration, that the static friction is also equal to mass times acceleration. Now, we know that the definition of static friction has that static friction can take up any value up until the value of mu sub s, the coefficient of static friction, multiplied by the normal force. So that means that the maximum value of static friction, which I could write like this, would be equal to mu sub s, which is 0.3, times the normal force, which we earlier calculated to be 4.905. So put that into your calculator, and you get 0.3 times 4.905 equals 1.47 newtons. That is the size of static friction. Or more correctly, that is the maximum size of static friction. The static friction can take up any value up until we reach 1.47 newtons. Plugging this information into F equals ma, we get 1.47 newtons is equal to mass, 0.5, times acceleration. So we can solve for the acceleration as 1.47 divided by 0.5, which is 2.94. This is the acceleration that is due to the static friction. It is the acceleration that's occurring in the x direction, and since this acceleration is causing this object to move in a circle, this is the centripetal acceleration. So in this case, the centripetal acceleration happens to be 2.94 meters per second squared, and I really should not put this I here. It just so happens that at this moment it's pointed in the I direction. But centripetal acceleration is also related to the maximum velocity, or more correctly, the maximum tangential velocity, So, since we know what the radius is, we can say 2.94 is equal to Vt squared over the radius, which is 0.2. So we can easily solve for Vt squared. 2.94 times the radius, 0.2, and then take the square root of that to find the velocity, 0.77. So the tangential velocity is equal to 0.77 meters per second. That is how fast this object is allowed to move before it will slip on this surface because you have exceeded static friction. This is a variant. It's called a conical pendulum. Again, the bob is tracing out a horizontal circle. Consider this situation. A 1 kilogram conical pendulum is tracing out a circle 0.1 meters in radius. The tension in the string is 15 newtons, and the string makes an angle of 25 degrees from the vertical. What is the velocity of the bob? Again, we will examine it at its leftmost position, and again, we will start with a picture. The free body diagram contains only two forces. The weight force pulls it down, and the tension force supports it. But the tension force is at an oblique angle. We need to break it into its components. When we break it into its components, we get a free body diagram that looks a little bit like the last example. The only force present is the horizontal component of tension, so that must be equal to mass times acceleration. We substitute for everything we know, and we find the value of acceleration. This is the centripetal acceleration, and it's equal to v squared over r. Substituting in for r, we find that v is equal to meters per second. A vertical circle is one where the height of the object is changing. In these cases, there can be multiple forces contributing to the centripetal force, and the velocity is generally not constant. An example is the famous trick of whirling a bucket of water over your head without the water spilling out. Consider this question. A 5 kilogram object is swung on a 0.75 meter rope. What is the minimum velocity it can have at the top if it completes the circle? We start off by drawing a picture. Now, what are the forces at the top of the circle? Clearly there's weight that's unavoidable. But how big is the tension? Well, in circular motion, acceleration is related to velocity. If we're talking about the minimum velocity, that must yield the minimum acceleration, which in turn means the minimum centripetal force, which means besides weight, there can be no other force at the peak. So the free body diagram contains weight. That's it. Let's do the force balance in y. The total force in y is now just the weight force. That's equal to mass times acceleration. We can easily solve for the weight force. It's 49.05 newtons. Set this equal to mass times acceleration and solve for the acceleration. We get an acceleration of 9.81 meters per second, and this makes sense because at this point the object is feeling only one force, gravity. But this acceleration is in turn equal to v squared over r. Since r is 0.75, we can solve for v. It is 2.71 meters per second. This is a legitimate way to solve this puzzle, but in a few videos we'll see a much easier way to solve it using work and energy. When you take an exit off the I-95 onto a smaller road, you often have to take a circular off-ramp. Have you ever noticed that the off-ramp is tilted? Here, the normal force from the road is providing an assist as you move in a circle. This is known as a banked curve, and it combines concepts from ramps and circular motion. Consider this situation. You are in a 1,000 kilogram car. You are on a circular off-ramp with a radius of 100 meters. It is banked at 5 degrees. What is your velocity? We start by drawing a picture and a free body diagram. We see there are only two forces, weight and normal force. This is the only ramp puzzle where we set the axes in line with the weight, not the normal force. When we do so, we see the normal force at an oblique angle, 5 degrees to be exact. So we have to break it into its components, and we see the logic for not tilting the axes as in other ramp puzzles. The normal force is responsible for the object moving in a circle. It is the centripetal force. So we must have a component in the x direction for it to operate as such. We'll set up the force balance in the y direction. The total force in y equals normal cos 5 degrees minus weight. The weight is easily found. It is 9,810 newtons. Applying this in the force balance, we can solve for the normal force, 9,847 newtons. What about the x direction? Well, the only force in x is normal sine theta. We substitute the normal force in and solve for the centripetal acceleration, 0.858 meters per second squared. Finally, the centripetal acceleration equals v squared over r. So once again, we substitute for what we know, and we get a velocity. In this video, we saw several examples of circular motion and the centripetal force that causes it. This concludes our discussion of forces. In the next video, we will begin a new chapter, work and energy.